Chapter 17, Groundwater. The importance of groundwater. Groundwater is water found in the pores of soil and sediment, plus narrow fractures in bedrock. Groundwater and the hydrosphere. 0.6% of the hydrosphere is groundwater. Groundwater is the largest reservoir of fresh water that is readily available to humans. Okay, so of Earth's fresh water, 85% is in ice sheets and glaciers. Now 14.6% is in groundwater. Okay. Around 94%, share of all liquid fresh water, because this includes water in vapor form, of all liquid fresh water, 94% is in groundwater, okay, and the other 6% is in rivers, atmospheres, form moisture, and lakes. Geologic importance. Groundwater acts as an erosional agent dissolving soluble bedrock such as limestone. Groundwater also serves as an equalizer of stream flow. Most groundwater soaks into the ground from precipitation. The zone of soil moisture is a zone where water is held by molecular attraction on soil particles in the near surface zone, used by plants. It evaporates directly back into the atmosphere. The zone of saturation is a zone where all the pore spaces are completely filled with water. Water in the zone of saturation is groundwater. The water table is the upper limit of the zone of saturation. The unsaturated zone, or Badose zone, is the area above the zone of saturation. Pore spaces include both air and water, include the zone of soil moisture, includes the capillary fringe, a region where groundwater is held in pore space by surface tension. Okay, so here we have our zone of saturation, and the water table is the top of the zone of saturation, all this darker area. Okay, and the top of that is the water table. Okay. Now, so here's our zone of saturation, and just at the top of it, this little area is called the capillary fringe, where surface tension holds moisture there. Then here's the unsaturated zone. There's mostly air in the pores, but also some water. And here is the zone of soil moisture. Variations in the water table. The depth is highly variable. It varies seasonally and from year to year. Precipitation variations affect the depth of the water table. The shape is usually a subdued replica of the surface topography. Interaction between groundwater and streams constitutes a basic link in the hydrologic cycle. Gaining streams gain water from the inflow of groundwater through the stream bed. The water table is higher than the stream surface. Now, losing streams moves water to groundwater system by outflow through the stream bed. It's when the water table is lower than the stream surface. Combination of gaining and losing streams. A stream can gain in subsections and lose in others. So here we have a stream. The water table is above the base of the stream, so it's gaining water from the groundwater. Here, this is a losing, let's see. Now here's a losing stream. The water table is below the bottom of the stream, so water is seeping through the stream bed into the groundwater. Porosity is a percentage of pore or open space in a rock or sediment. That's called porosity. Depending on the size and shape of the grains, how well they are sorted, and how tightly they are packed, it gives this amount of porosity. Poorly sorted sediments have very low porosity. This determines how much groundwater can be stored. So here, the beaker to the left is filled with 1,000 milliliters of sediment. The beaker on the right is filled with 1,000 milliliters of water. Now, if we pour water into the sediment-filled beaker now contains 50 milliliters of water. The pore space must be 50% of the volume of the sediment. Okay, so 1,000 milliliters, 500 milliliters of water divided by 1,000 milliliters, and we get 50%. Permeability, aquatards, and aquifers. Okay, so this is influencing the storage and movement of groundwater. Permeability is the ability of a material to transmit a fluid. So this depends on the connectivity between the pore spaces. An aquatard is an impermeable layer that hinders or prevents water movement, for example, clay. An aquifer is a permeable rock strata or sediment that transmits groundwater freely. So sands and gravels are good examples. Groundwater moves very slow. The average rate is about 4 centimeters per day. Simple groundwater flow system. The force of gravity and pressure differences move groundwater. Groundwater is replenished in areas of recharge. Groundwater flows back to the surface in the discharge area. So here we have for groundwater movement. So here's our water table. Okay, this is a recharge area, water that infiltrates into the ground to add water to the groundwater. The discharge area is area where the stream is gaining water from the groundwater. Okay, here's a zone of recharge, and here's another discharge area. Measuring groundwater movement. Darcy's law is a measure of the volume of water that flows through an aquifer using the hydraulic gradient, connectivity, and cross-sectional area. Hydraulic gradient is the water table slope. The hydraulic connectivity takes into account the permeability of the aquifer and the viscosity of the liquid to determine how fast water will flow through a medium. Okay, so here we have our hydraulic gradient, is that slope of the surface here. So we take h1, or the height up here, and subtract from it the height down here to get that. And we divide that by d to get the hydraulic gradient. Different scales of movement. The area of groundwater flow systems vary from a few square kilometers to tens of thousands of square kilometers. Regional groundwater systems interact with deeper, larger groundwater systems. So here we have a groundwater flow system. So we have some. So here's our high connectivity aquifers, this darker blue area. Our low connectivity areas are our aquitard units. And our water table is up here. Okay. So here's our major direction of groundwater movement in a deep regional system, or these black arrows. Groundwater movement in our sub-regional system. But our near surface local systems are these blue areas, showing our recharge and discharge areas. A well is a hole bored into the zone of saturation. Most common methods for removing groundwater. Drawdown, as water is withdrawn from the well, the surrounding water table is lowered. That forms the shape of a cone. We call it the cone of depression that forms around the well. So here, in this farm, they had two little wells. As they pumped the water table is drawn down, forming this cone shape. Okay. Then I put a new well in, because we're going to put a high volume irrigation system in, and this one is deeper and it pumps a lot more water out. It's going to form a very large cone of depression, so large that the old wells are now going to be dry wells because we're not deep enough to reach the new groundwater table. An artesian system, artesian well or spring, is a system where groundwater under pressure rises above the level of the aquifer. Water must be confined to an inclined aquifer. Aquitards must exist above and below the aquifer to confine it, and an aquifer confined by aquitards is called a confined aquifer. Okay, so a non-flowing artesian well, the pressure surface is below the ground level. A flowing artesian well, the pressure surface is above the ground. Not all artesian systems are wells. Artesian springs also exist. So here we have between two aquitard layers or confined aquifer, and it's at an incline, it's sloped. Okay, so there's an H1 and H2 we can measure. Okay, there's a hydraulic gradient here. Now the pressure that this water is under, instead of having a water table, it's a pressure surface. So all the pressure it's under, because there's water constantly being added into the system, that pressure surface is up above the ground level here. Now, if you were to drill a well here, the top of that well is above the pressure surface. So the water will rise up as far as the pressure surface, but you'd still need a pump to get that water out. Down here, where the top of the well is below the pressure surface, the water will freely flow all the way up and out of that well. Some artesian systems transmit water at a great distance. For example, South Dakota. Municipal water towers create an artificial artesian system. Okay. So here's a classic artesian system. So this is South Dakota with the Missouri River in the middle. Here's the Missouri River. So here's this confining layer. Okay, and so this is our recharge area. Okay, and these various layers are our aquifer. Okay, so water's going to recharge here. It's going to be under pressure. And here's going to be where area of flowing artesian wells. Okay, in this case we have the water tank, the local city's water tank. It's raising water way up high, so you have a high pressure surface. So the water gravity flows this way, and so when you open up your valves for your water, your sink, water is under pressure, so it's going to move that water through the pipe and up and out. So pressure surface is way up high. Springs, the natural outflow of water from the intersection of water table and the ground surface is called a spring. Here, the area 1000 springs. So here it's outcropping of the groundwater surface, and water is freely flowing out of the groundwater here in the spring. Hot springs, when water in a hot spring is 6 degrees Celsius to 9 degrees Celsius warmer than the average annual air temperature of the area. The water from the most hot springs is heated by the cooling of igneous rock. Some hot springs water is warmed by geothermal gradient. The main hot springs include this one in Iceland, are associated with areas that have experienced recent igneous activity. Geysers are intermittent hot springs in which columns of water erupt with force. How geysers work? They occur where extensive underground chambers exist within hot igneous rock. Groundwater heats, expands, changes to steam, and then erupts. So here we have our deep cavern of water. There's a lot of heat coming in from below. That water gets converted into steam, and it basically erupts through this channel, and you have this geyser eruption. Eventually this will fill again with water, and the cycle will go again. Geyser deposits. Chemical sedimentary rock accumulates at the surface. The type of rock reflects the chemical makeup of the bedrock. Siliceous sinter or geyserite forms from dissolved silica. Travertine forms from dissolved calcium carbonate. Here's Yellowstone Mammoth hot springs. You see lots of deposits of mineral matter. Mining groundwater. Treating groundwater is a non-renewable resource. In many places, the water available to recharge aquifers is significantly short of the amount being withdrawn. For example, the High Plains Aquifer. So here's the High Plains Aquifer system. It covers many states in South Dakota and Wyoming, Nebraska, Kansas, Colorado, New Mexico, Texas, and Oklahoma. Okay. The amount of storage, water stored in this aquifer, USGS, may have declined to over 200 million acre feet, or over 65 trillion gallons in the past 60 years. Subsidence, the ground sinks when water is pumped from wells faster than natural recharge processes can replace it, because the pore spaces don't, instead of having water, just have air in them. Those pore spaces start to collapse when there's weight above them, and it causes subsidence. So one example is the San Joaquin Valley in California, where back in 1925 the ground surface was all the way up here before it started doing heavy groundwater pumping. And then once they started pumping for agriculture, subsidence occurred. In 1955 the surface was up here, okay, and now in 1977 it's all the way down here. So 30 feet of difference after 52 years of heavy pumping. Saltwater contamination. Excessive groundwater withdrawal causes salt water to be drawn into wells, thus contaminating fresh water supply. Can correct the problem by using recharge wells, primarily a problem in coastal areas. So here we have our freshwater groundwater here, and under the ocean we have our salt groundwater. It's denser, it's kind of sunk underneath. But if you start over pumping, you're going to not just draw down the fresh water, but you're going to eventually start sucking up salt water. One common source of groundwater contamination is sewage. Extremely permeable aquifers, coarse gravel ones, have such large openings that groundwater may travel long distances without being cleaned. Sewage often becomes purified as it passes through a few dozen meters of an aquifer composed of sand or permeable sandstone. So comparing two aquifers, so here we have a house with a septic tank that's contaminating the water, okay? And this looks like a limestone aquifer with large caverns and pore spaces, and the days to weeks this water travels, okay? So the water can still be contaminated when the next well sucks it up, okay? Down here we have our septic tank contaminating water, but it's in a sandstone aquifer, and the water is going to travel much slower, so it's going to get purified before it gets to this well to be pumped up. Sinking a well can lead to groundwater pollution problems. The cone of depression will locally increase or reverse the slope of the water table. Other sources and types of contamination include highway salt, fertilizers, pesticides, chemicals, and industrial materials. Okay, so changing of direction, well, let's see, with the outflow, septic tank goes this way, away from the well, okay, and the well has a cone of depressions from pumping water, but then we stop pumping water, okay, that water table is going to rise up and the septic contamination is going to flow toward that small well. So, but this actually this change in direction is caused because we put a larger well here and we're pumping heavily. So this cone of depression is actually sinking more, and it's going to basically be sucking that contamination back up the old well. Other sources, fertilizer, garbage, and just sedimentation of construction. The groundwater dissolves rock. Most groundwater is often mildly acidic, contains weak carbonic acid, forms when rainwater dissolves carbon dioxide from the air and from decaying plants. Carbonic acid reacts with the calcite and limestone to form calcium bicarbonate, a soluble material. So caverns are created by acidic groundwater dissolving soluble rock. About 17,000 caves have been discovered in the United States. Cavern development develops as acidic groundwater dissolves limestone bedrock, and development occurs at several levels. Most active erosion is at or just below the zone of saturation. How dripstone forms: calcium carbonate deposits dripping water, and that dripping water evaporates and leaves behind evaporates, called travertine. Dripstone features are speleothems. Speleothem is a general name for all dripstone features, but these include stalactites that hang from the ceiling and stalagmites that form on the floor. So here's some stalactites and some stalagmites, and this is a column. Karst topography is a landscape that's been shaped mainly by dissolving power of groundwater. Some common features include irregular terrain, sinkholes or sinks formed by groundwater slowly dissolving the bedrock, often accompanied by collapse, and striking lack of surface drainage, streams. So here we have our groundwater limestone area. We have a stream here and a few sinkholes. Then over time, more and more caverns will form, and they will collapse, forming more sinkholes. And this stream is going to start collapsing. This stream's cutting down, and you're going to end up with more caverns and larger sinkholes, and solution valleys will form. Let's end that chapter.